Okay, thank you very much. So, so let me start. I want to start by, thank you, yeah, that's it. I want to start by telling you a story tonight. And it's a story of how quasars were discovered. So, let's start with this. So, this up here that you see, it is the electromagnetic spectrum. So, it's the range of wavelengths and frequencies that light can have. And you may recognize some names here to that we give to the different regions of this spectrum, like gamma, X-rays, UV, visible, infrared, and so on. And I mean, astronomy today essentially is just a collection, a fleet of telescopes that span the entirety of this electromagnetic spectrum, right? Each of these telescopes is looking at a different window in this spectrum, and by putting together all the information that we get from these telescopes, we are trying to understand the universe. But of course, this has not always been like that, right? For more than 2,000 years, the only way we've been able to do astronomy, right, was essentially by looking at this very small window in the spectrum, which is the visible window. So the light we can actually see with our naked eyes and with the optical telescopes. And then, sometime in the last century, well, a new window has been opened for the very first time, and that is the window in the radio band. Well, why the radio? Well, just because this is the only other region that we can directly access from Earth, as you can see from this diagram here. And so astronomers in the 40s and 50s started building these new radio telescopes, and they started pointing them to the sky. And essentially, what they try to look at is the sky in the radio band. And I mean, it's no surprise that the sky in the radio band looks a lot different than the sky we're used to, right? There are all these different sources, which are like sources that are bright in the radio. And so we started essentially catalogating these sources and asking, well, what are these sources? Where is this radio emission coming from? And the best way we have to answer this question is, well, to go back to the sky we are used to, so the sky in the optical, right? And to see where this radio emission is originating. And so in this way, we discover that many of these radio sources are actually galaxies that are also, emitting radiation in the radio band. But then, some other sources were actually way more puzzling. Take this source, for example. This is the radio source 3C273. And when we look at the optical sky, what we see, the source that we see in the optical looks just like a star. You see there's no difference between essentially all the other stars in the sky and this particular object that is emitting so much radio. The only difference is that stars are not bright in the radio usually. And so astronomers were very confused by these objects that they were finding, essentially that they just looked like stars, but then they were bright in the radio band. And so they started calling these sources quasi-stellar radio sources, which was then abbreviated in quasars. Now, if we don't understand the source, one of the best ways we have in astronomy to start is to get a spectrum of the source, right? And a spectrum, well, we've seen some spectra already in the introduction. Well, the spectrum is just that we take the light from the source and we pass it through a prism or something that gives us the intensity of the light at different wavelengths. And so this is exactly what astronomer Martin Schmidt, who actually did his PhD here in Leiden, did for this source in 1963. So he took this particular source, 3C273, and we took an optical spectrum of this source. And this is actually the original spectrum we took. And this, at the bottom, is some comparison spectrum, essentially, that shows all the emission lines that we expect from atomic transition. So this is, you can think about this as the expectation in terms of emission lines. And you see already that there is something quite surprising because we see some lines in this spectrum at the top, but they don't correspond to any lines that we were expecting at the bottom. So there is something puzzling here. There are these mysterious lines that we cannot really explain. And in general, the overall shape of this spectrum is something very weird that we've never seen before. And so, well, this was a very enigmatic observation until, Martin, while playing around with the spectrum, he realized something very important. He realized that these lines, well, they're not mysterious lines. They're actually the most basic lines that we see in the universe. They come from the hydrogen atom, but they are just not at the right place. They're all shifted to the red wavelengths of the spectrum. They're all by the same amount. In other words, they are all red shifted. Now, if you come to these scientific talks before, you may have noticed that, you may have noticed that the word redshift comes up a lot. And the reason is that, because of the expansion of the universe, all the sources that are very far away from us, well, they're all red-shifted. This is called cosmological redshift, and you can see like a little diagram of this phenomenon here. So this is the spectrum of a star that is very close to us, and you see all these lines here. And then we go to a galaxy that is, farther away, and you see that essentially all the lines are still there, but they're all shifted towards the redder wavelengths. And when we go to, and this redshift effect, well, it gets stronger and stronger the farthest galaxies are. And so essentially, the redshift is also a measure of the distance between us and the thing we are looking. Now, astronomers at the time knew about this redshift effect, but they had found some galaxies that were like a little bit redshifted, but they were definitely not expecting to find this redshift effect in quasars, because everyone was expecting quasars to be some weird stars in our galaxy, right? And instead, if this redshift effect was true, well, it meant that quasars were actually among the most distant objects we knew in the universe. Now, this is a pretty huge discovery, right? And indeed, it made it to the cover of the time. And it brings with it very important consequences. Well, one consequence is that, quasars look just like stars in the sky, right? But stars are super close to us, whereas quasars are extremely far away. So the only possible explanation for this is that quasars are extremely bright objects. They are indeed 100 to 1,000 times brighter than the luminosity of entire galaxies. And the other important consequence actually comes from another observation. It is the observation that actually the light from quasars changes a lot over time. Quasars are flickering very fast, as you see from this animation here. And these allow astronomers to place constraints on the size of these quasars, on the size of the region that is emitting this radiation. And astronomers found that quasars are actually very compact. They are not much larger than our solar system. And so these are all pieces of the puzzle that astronomers needed to put together at the time, right? And so obviously all of these sparked a huge debate in the astronomical community. So what are quasars really? What are these sources that are so bright and so small, so compact? And all kinds of hypotheses were proposed. From the most exotic hypothesis, maybe it's sign of new physics we didn't know about, and we had no idea, to more like standard hypotheses, maybe there's just some kind of extreme supernova events, or the gravitationally lensed galaxies. Some people were even refusing to accept that the redshift of quasars was actually due to the expansion of the universe, and they were saying maybe quasars, the redshift was due to something else. If quasars are kicked out of the galaxy very fast, and they're moving very fast away from us, that also creates a redshift, and gravity can also create some redshift effect. And so these were all hypotheses that were proposed, and there was a very big debate. And the correct answer to this question was actually proposed 1 year later, the discovery of quasars. But it took, I think, 20 years to the entire community to fully acknowledge that that was the right answer. And the right answer is that quasars are actually, the right answer is not coming up, okay. Is that quasars are actually supermassive black holes accreting at the center of galaxies. So today, we know that a quasar is just a supermassive black hole. So it is a black hole that is extremely massive, 1 million to 1 billion times more massive than our sun. And this black hole that you see at the center here, it is accreting a lot of material around it. The material spirals towards the black hole and falls inside the black hole. A lot of material. When I say a lot, I mean up to 100 Earth masses of gas per minute. And this gas, while spiraling inside, it is heated up to such temperatures that it emits a huge amount of radiation. So today we know what a quasar is. And we've also understood a lot about quasars. One thing we've discovered is that we found quasars at all kinds of redshifts. You remember 3C273? That was the first quasars discovered. Well, the redshift of that quasar was around 0.15. Now, we found the quasars in the years later. We found quasars at redshift 1, 2, 3, 4, 5, 6, 7, and we're going towards 8. And so this means that we found quasars farther and farther away from us. And this also means, since light takes time to arrive to us, this also means that we've been exploring like a time that was earlier and earlier in the history of the universe. And in particular, the frontier of quasar discovery now is studying the very young universe. So these very early quasars in this very young universe, when the universe was just a few 100 million years old. And of course, these very young quasars tells us a lot about the young universe, and they also tell us how the first supermassive black holes formed and evolved. Not only that, we also mapped out the distribution of quasars. We have counted quasars in the sky, and we have found out, essentially, that quasars are actually way more abundant than we thought. This is essentially the quasars that are nearby. So 3C273, the first quasar, was actually very close to us, right? And we found that this population is actually just the tip of the iceberg of the quasar population. Because if you follow the evolution, well, the evolution tells us that today quasars are actually very rare objects. And when we go back in time, so farther and farther away from us, well, then there is an age that was around 10 billion years ago that we call the golden age for quasar activity. Quasars were way more abundant back then than today. And once we go to the very young universe, so extremely far away, quasars become rare again. Now, this has an important consequence, which is, well, if quasars were so abundant in this golden age of quasar activity, well, remember, quasars are supermassive black holes that are growing a lot of mass. But if quasars were so abundant, then this means that, well, supermassive black holes were also abundant, and they were also growing a lot of mass. And so this means that supermassive black holes should be everywhere, right? And indeed, when we look at the galaxies around us today, well, you may know that every time we look at a massive galaxy, we find signs of a supermassive black hole in its center. And these supermassive black holes are there, we've actually imaged them, right? Well, they grew their mass while growing as quasars, and probably they grew their mass during this golden age of quasar activity. So I would say that if I have to summarize this, well, chapter with a sentence, there would be the advent of radio astronomy in the 50s has led to the discovery of a new abundant population, quasars, which has revolutionized our understanding of the role played by supermassive black holes in the universe. So this is, well, I guess, chapter 1. Now I want to go back to this and, well, introduce a new object in the fleet, which is the James Webb Space Telescope, or JWST. JWST was launched at the end of 2021, and it is an infrared telescope. So it joined the fleet of telescopes and is observing these around these wavelengths here. Now, there were other telescopes in the infrared, but JWST is just so much better than everything we've seen before at these wavelengths that it is like opening a new window in the universe. And so just like a radio window brought us revealed the existence of quasars, well, JWST is also a new window, this time in the infrared. And this is what the JWST sky looks like. Well, there are some objects that you may recognize, stars, there are a lot of galaxies all around, but as every time we open a new window in the universe, there are also very surprising discoveries. And in this case, one of the most surprising discoveries that JWST has brought us, I would say, is this population of objects here. You see them as, these very red, very point-like objects, so little dots. They're red, they're little, we'll call them little red dots. And we started cataloging them. They're everywhere. We didn't see them before JWST, and now that we have JWST, they're just everywhere. In every JWST point, you see there's so many. And we started cataloging them, and we started studying them. We know now that these little dots are, of course, red and little. They're also abundant, and they're also very distant. This time we know about redshift, and so we know that the redshift is very large. They are in the young, we only find them in the young universe. Also, probably the most interesting property is that, they show signs of broad emission line in the spectrum. So we've taken a spectrum of these little dots, just like we did with quasars back then, and they show broad emission lines. Why are broad emission lines interesting? Because that's a property they share exactly with quasars. So you see this quasar here, you remember 3C273? Well, this is the spectrum, so the intensity as a function of wavelength, just plotted in another way. And you see that all these lines are not spikes, they're pretty broad. And these broad lines are just created by gas that is essentially rotating very fast around the supermassive black hole. And this fast rotation is moving the gas in wavelength around the line, so that the line is not a spike anymore, but it becomes a some broad emission. Now, so this is just to say that broad lines are just a sign of a supermassive black hole that is there at the center, and some gas that is rotating very fast around the supermassive black hole. So that suggests that little dots may have may have a lot in common with quasars. But then when we look at the overall spectrum, this is the spectrum of a quasar, right? And the spectrum of a little dot is completely different. Once again, we have a population of sources whose spectrum we don't understand at all. We've never seen anything like that. And so, I guess this, once again, has sparked a huge debate among the astronomical community. What is a little dot then? And there are a lot of hypotheses. Well, this time I cannot tell you which is the right answer, because no one knows. I guess, you can see all kind of different hypotheses there, from things related to black holes, self-interacting dark matter, brown dwarfs. There's so many, right? I guess the most interesting thing to me is that, many of these hypotheses involve the presence of a black hole, because there are signs that a black hole may be there, right? And indeed, this has big consequences. In particular, you remember this plot of the evolution of quasars with redshift and evolution across the history of the universe, right? There was this golden age of quasar activity, and then in the young universe, quasars were very rare. Well, if little dots are accreting supermassive black holes, this may rewrite the history in the young universe completely, because they are so abundant that they are just up here in terms of abundance. And so we need to rethink what we know about supermassive black hole accretion in the young universe completely. So I guess this brings me to the end of the talk. And I guess this allows us to write a new chapter, I guess, in this story. And the chapter, I would write something like that. The advent of JWST in the 2020s has led to the discovery of a new abundant population, the little red dots, which may once more reshape our understanding of supermassive black holes and their evolution in the young universe. But of course, we need to put a big disclaimer here, because the full story here is definitely yet to be written. So with that, I thank you for your
Thank you, Elia. That was a very wonderful talk. Now it's time for questions. So, anybody?
Just a question for clarification. You have a black hole and all this stuff comes into it and it shines. Is that a process that goes on forever, or is at one point in time the space around it empty and it stops to shine?
Yeah, that's a very, very interesting question. It is more like the second thing you said. So indeed, we think, well, all we can see is quasars in the universe, right? So like we cannot go to a quasar and play the movie of its history. We only see that at some point, right? But we can run simulations. We can try to understand how things evolve. And indeed, we think that, well, quasars can actually start, like the fact that the black holes continue accreting, at some point they run out of gas. And, well, they stop accreting, and so they stop the quasar process. Not only that, we think that quasars, with their activity, they can actually starve out entire galaxies. So they can actually, well, through different channels, they can stop, they can push away gas, or they can make this gas warm, so that entire galaxy run out of fuel for star formation. So not only quasars in some ways starve themselves, they can also starve the entire galaxy around them.
Yes, so what is, so thank you for your talk. As I understand, there are some hypotheses for what the little red dots are. What is your favorite hypothesis?
Yeah, that's a very good question. So, what's my favorite hypothesis? I think we just don't know. I think so. I would like to say that there are black holes, because that would be very cool, I guess, and very that would indeed have big consequences, right? But I mean, as I was saying, it took 20 years for the community to reach an agreement on what quasars are. We are just 2 years into the process, so I would give ourselves some time before we reach any final conclusion. I think we're just not there, to be honest. I think there are so many properties that we don't understand, and this is part of the process, right? Like people make up hypotheses, but these hypotheses explain only a part of the problem, and I think there's not a single hypothesis so far that can explain everything we are observing.
You had one special black hole on the upper right. What sort of black hole was that?
Oh, let me pull it up, maybe. You mean...
from the hypothesis.
Oh, okay. Can you go back? Sorry. It's like towards the end. Yeah, you can bring me to the end and then... Yeah, okay. So, here, right?
The Super Eddington black hole.
Yes, okay. So, yeah, okay. So, Super Eddington is a physical concept. It means that we think there is a limit to how much the black holes can eat, essentially. So, I was saying they can eat up to 100 Earth masses of gas per minute, right? That's a lot, right? But we think there is a theoretical limit, because at some point, the pressure from the black hole itself becomes so much that it pushes the gas away. And so no further accretion is allowed. So there is this theoretical limit. One possibility, there are speculations, we have reason to think that there are ways to go above this theoretical limit. And so that would essentially create an accretive black holes with some signatures, some observational features that we didn't know before, simply because it is a completely new way to accrete, to swallow gas, right? And so this super Eddington just means that they're essentially black holes that are accreting so much that they are above this theoretical limit. They accrete more than this theoretical limit, and then can create essentially observationally. That would mean that their spectrum looks very different from the one of quasars that are below the theoretical limit, and it would mean that they have so many different properties, right? And so that would explain why these little dots are so peculiar.
Thanks.
Okay.
Just quickly, what's the green pea equivalent?
Oh yeah. So good question. So what's the green pea equivalent? So as you probably understood, astronomers try to have fun with names and things. Green pea, I think it's a population of objects that are well compact as little red dots, but they're green. they appear green in particular in another telescope, which is the Hubble Space Telescope. So they have slightly different properties, and they appear not in the early universe. So like little red dots, thank you. Little red dots are in the early universe, right? So these in this region here. Green peas are more very close to us. So they're more in the universe that is around us. And so they have different properties, but some people are speculating that maybe, like if we see these green peas here, then they are the same objects, but they will look in the young universe they will look as little red dots. So okay.
To my best understanding, the observation about the little red dots is made by radiological, like, what is it, telescopes, is it?
It is made by the James Webb Space. It's only made by this James Webb Space Telescope that I talked about, right? This, this one.
And my question then is, have you tried to observe, or have you made the observation or overlaid it to any other type of telescopes, and were you able to locate the same spaces or not?
Very, very good question. So the question is, if we see little red dots with the JWST, right, can we see whether we see them with other telescopes as something else, maybe like for example, quasars, we saw them in the radio, but we also saw them in the optical, right? Well, we tried, and one of the biggest problems with these little red dots is that we don't see them in any other telescopes, or not in ways that are useful. So we search them in the radio, there's no sign of them. We search them in the X-rays, there's no sign of them. So if we find them, that would be useful because we could understand a lot, right, by like comparing them across different regions of the spectrum. But we're not finding them, and that is indeed one of the most the biggest obstacles, I would say, to getting to the final answer.
Just in that diagram, how high does a plane have to fly to be able to do infrared astronomy?
Sorry, can you repeat the question?
How high must a plane fly to be able to do infrared astronomy?
Oh, that is a good question, which I'm not sure, but I think the height at which infrared radiation is blocked is this stratosphere. And I do not think planes can go at that high, unfortunately. I think normally planes fly around 10 kilometers or so, and the stratosphere it's a few times higher. I think it's about 50 kilometers. I'm not sure about that, but I think there's definitely we would need something that goes more towards space than planes. I'm not sure people have tried, especially as you see, to fly planes and to telescope into planes. But I think that it's just more convenient at that point to fly things into space because they last longer and they're more efficient once they go out of here. Right? They can just stay there for many years.
Up here. So you're saying that the red dots are quite abundant. Like what likelihood, or what is the share, let's say, when we're comparing to what is in normal optical vision, for example?
Yeah, so when I see that they're quite abundant, I mean that we find them, we find many of them in the sky in general. So if we look at a small region of the sky, there's many of them. To give you a number, they're not as abundant as galaxies. Galaxies are everywhere, right? Like if I take this plot here. Okay, getting there. Okay, yeah. If I take this plot here, all of them are galaxies, right? So galaxies are everywhere. They're way more abundant than little dots. About 1% of the galaxies can be little dots. So it's like out of 100 galaxies, we on average see one little dot, and this is essentially more abundant than quasars, because quasars are even like it's even less than out of 100 galaxies we see one quasar, and that's why essentially when we go to these other plots here we need to we need to essentially getting there. Oh sorry, it's longer than expected. Okay, yeah, they're essentially way more than we thought when we looked only at quasars.
Thank you.
Because
So you've drawn the analogy between quasars and little red dots. Now quasars have reshaped our understanding of galaxy formation and do you expect that in 20 years' time, when you'll look back, that little red dots have done the same? Especially because they're more abundant now?
Yeah, very good question. I think they will. I would say it depends on what they are, like, they definitely play a role in galaxy formation in general, just as we've learned that quasars play a role in galaxy formation, right? They're not just interesting by themselves, but quasars can start galaxies and can play a role in the overall evolution of the universe. So yes, little dots are as abundant, and especially I would say they play a role. They probably play a role in reshaping the young universe. Right? When we get to the mature universe towards this golden age for quasars, little dots are probably not as important anymore. But when we talk about reshaping galaxies and our understanding of galaxy evolution in general, I would say in the young universe, yes, very likely.
Hi. If you're looking at today and looking back at the two red dots, do we know if they're still active? That's my first question. Second question is, when we see those little red dots, do we know if they come from the accretion disk or the jets?
Okay, so the first question is if they're still active today. That's your first question, sorry? Did I understand correctly? Yes, the answer is we don't really know. People are trying to look into that a lot because, I mean, finding some little, like the obvious thing that's extremely interesting is that if we find a little dot that's very close to us, that's much better to study, right? Like it's very close to us, so we can see it we can see it in so much more detail, and that's super cool. So yes, people are looking into finding little dots in the very nearby universe. Maybe we've found something, but people are still speculating. It's not clear. Maybe we indeed have found a couple of little dots here, but they're like the thing we can say is that it's very likely that little dots are very abundant in the young universe and then they stop being abundant. They drop very fast. And when we go here, just as quasars, they are very rare. So we may have found some little dots in the very local universe around us. But if they're there, they're very rare, and we don't expect them to be very abundant in the local universe in general. Your second question about whether the light comes from the accretion disk or the jet, that also we don't know. Because we cannot explain the spectrum in general, right? We have this spectrum that we observe, but unfortunately we cannot explain it. So that we could tell whether they would come from the disk or from the jet if we could explain the spectrum. In general, the jet is associated with more with the wavelengths, such as radio or X-rays, where we don't see little dots. So it's unlikely that the radiation from little dots is coming from the jets. I would say between the two is more likely that it's the accretion disk, but we don't know yet.
Hello, thank you for a great talk. I'm curious about, is there a link between black holes and gravity?
Indeed there is.
Can you explain it simply?
Of course, yeah, I'll try, I'll do my best. So, I mean, black holes, like if you think it like in the most basic way possible, the way you can think about a black hole is light cannot escape, right? And that is because of gravity. So essentially the gravitational pull of a black hole is so intense that the light, even light, is not able to escape it. And so that is why we call it a black hole, because I mean it's black in the sense that light cannot get away. You may ask why are quasars so bright if a black hole, if light cannot escape a black hole? The answer is that the light comes before the gas falls inside the black hole. So the light, the gas is going going towards the black hole, and it emits all the light before it is swallowed by the black hole. And so after it is swallowed, no light comes out, right? After the gas is inside, there's no way it can come out. But before it gets into the black hole, it's emitting a huge amount of radiation.